Today, what we want to talk about is basically what happened to this. Okay. Somehow, okay, I think I've messed this up. I shouldn't do this, but anyway. The maximization isn't working apparently. Okay, you can see the white page, right?
Yes,
Yes,
we
sir.
can.
Uh, just leaving a small bit peeking from a side just to make sure that I can still see whether I'm connected or not. Okay, and what we are going to talk about today are continuous groups. And mostly we will talk about Lie groups. Now, so far, all the groups that we have talked about have been finite groups, elements, the number groups for which the number of elements is finite. Now, what I'm going to talk about today is a special kind of infinite group. And although continuous groups and Lie groups are really not identical things, Lie groups are a subclass of continuous groups. For us, especially in physics, the only kind of continuous groups that we will really be interested in are Lie groups. So for us, the two words will sort of be synonymous. Now, I could have started by giving you an example of continuous Lie groups and then talked about their general properties later, but I'm pretty sure at least two groups of this kind are pretty familiar to you already. One is SO2, right? Rotations in two dimensions. And the other is SO3, which of course are rotations in three dimensions. Now, we are going to have a lot more to say about these two groups and their specific features simply because they happen to be, along with, say, SU2 and SU3, perhaps the single most, okay, not the single most, but the most important groups that you will ever talk about, at least most important Lie groups that you're going to talk about in physics. However, what I'm going to do today is start from a general viewpoint. We will talk about general Lie groups. And from once we get the general results down, we are going to look at SO2, SO3, maybe later SU2, SU3, etc. Also as specific examples of what we are talking about. Okay, having said that, it would have been great if all of you had been in my differential geometry class last semester. Many of you were, but I'm not sure all of you were. Or it would have been great if I had enough time in the differential geometry class last semester to talk about Lie groups. Basically because the things that we talked about in differential geometry in that class, the major object that we talked about were manifolds, right? And Lie groups are basically groups which are manifolds. Now, what exactly do I mean by that? I'm not going to talk about manifolds in detail today because some of you may not have been subjected to, or at least tormented by me in the last course. So, but anyway, basically a manifold is any set. Okay, I wanted to draw a wiggly line. Okay, wiggly, this is fine. M, which is locally, at least if you look at small patches of that, that looks like some Rn. In other words, if you look at a small enough patch of a manifold, you can put n real coordinates on that so that when you tell me what those n coordinates are, I can tell you exactly which point on the manifold you're talking about, and vice versa. That is, If you give me a point here, I will be able to give you n real numbers. If you give me the n real numbers, I will be able to give you back the point. That, of course, is what we call a choice of coordinates in basic physics. And that exactly is what a continuous or a Lie group is for us. Basically, a group where elements can be characterized by, well, bunch of real numbers, which we can choose to call coordinates. We usually call them parameters. Okay, we don't call them coordinates just because it's not usual to call them coordinates. That's it. Otherwise, in any differentiable manifold, you have a choice of coordinate system, just like we have a choice of coordinate system in our daily life world. And just like in any such coordinate such situation, you have a bunch of coordinates talking about points in the space. Lie groups are just like that. You have coordinates for each points in space. It's just a matter of nomenclature that we usually call those points parameters, or those numbers, sorry, those real numbers parameters. The points are the group elements. So typically you will have something like this, some group G, and typically one important point that we will always talk about is the identity. And for the time being, let's look at what happens close to the identity. The basic idea is close to the identity, there will always be some region, let's call that N, some neighborhood of the identity, where every point that you have, say each point, of course, talks about a group element. So E is a point here, A is a point, B is a point. These are all group elements. Each point, that's a typical group element G, will be mapped by some mapping, let's call that phi, to a bunch of real numbers. How many real numbers? In fact, that number is called the order of the Lie group, or the dimension of the Lie group. Here, it's typical to call that number small r rather than n, which is usual in the language of manifolds. So this statement in the language of differentiable manifolds, it would be that Lie group is a differentiable manifold of dimension r. For us, all that matters is there is a way to assign to each element of this group, at least each element within this small, some neighborhood around the origin, around the identity, a bunch of real numbers. Let's call them, say, xi1, xi2, up to xi r. So typically we will say A, for example, this group element. Let's say A will correspond to alpha 1, alpha 2, alpha r. B will correspond to beta 1, beta 2, beta r. And very often, instead of talking about the group element, we will talk about the parameters. Now, that's not really very surprising. When we say a point, say 3, 4, 3i plus 4j plus 5k, we are actually specifying the coordinates of the point, and we are treating the coordinates, the numbers 3, 4, 5, as synonymous to the point itself. Just in the same way, in a Lie group, we will have R parameters specifying a group element, and each of these R parameters, once you specify them, you have told me which group element you're talking about. So instead of talking of the group element, we will typically talk about the parameters. Now, one specific choice that is always made, this is a convention, but is always followed, is that you choose your parameters in such a way that the identity always gets a bunch of parameters which are all zeros. So it's a null vector in the corresponding R dimensional space. Okay, so far? Any questions? Now, you must also realize one thing. Just like we can choose different coordinate systems, you can, of course, reparameterize elements in Lie group. Instead of using this particular chart phi or this particular map phi to map G or A or B to the corresponding bunch of numbers, you could also choose an entirely different chart. Now, of course, if you choose your chart differently, you're going to get a different bunch of numbers. You'll still get R numbers, R real numbers, but these real numbers could be very different from the numbers you had before. But the properties of the group which are really important, they should survive this change of chart. Okay. So some of the things that we are going to talk about will be dependent on having chosen a specific chart, but all the important results ultimately will turn out to be independent of the particular chart chosen. Simply because, as in ordinary physics, the way a physical system behaves should not really depend on the coordinate system you choose. But of course, one coordinate system may very well make the description of the physical system much easier. And you will also see there are very special choices of coordinate systems in groups, which makes the description of group elements much, much easier. But we will come to that later. Now, one immediate consequence of having something like this is, suppose you have this group relation AB equals C. Then, if you give me these bunch of numbers and this bunch of numbers, I know what A and B are. I know what the group is, presumably. So I should be able to tell you what C is, right? In particular, I should be able to tell you what the parameters for C are going to be. Yeah. In other words, if I know alpha 1, alpha 2 up to alpha R and beta 1, beta 2 up to beta R, I actually should be able to give you each one of the gamma 1, gamma 2 up to gamma R, right? In other words, the group multiplication table, where you tell me if I multiply two elements, this is what I'm going to get, essentially gets replaced by this. I need a rule which tells me, given a bunch of parameters for one element, another bunch of parameters for another element, what are the parameters for the composite element A times B? So basically what we have are something looking like this. Gamma, okay, not gamma, not one gamma, gamma 1, gamma 2 up to gamma R. So let's say gamma J typically will be some function Fj of what? What will it be a function of?
Alphas and betas.
All the alphas and all the betas, right? So it will be alpha 1 to alpha R and beta 1 to beta R. I'm just using a semicolon to separate the alphas with the betas, the parameters of A with the parameter from the parameters of B, right? Okay, you write this is looks very nasty. So what you use is typically the much shorthand version of this, which is gamma equals f of alpha semicolon beta. Where what you actually mean is alpha here stands for all the R numbers, beta stands for all the R numbers here. And when you write this as a single equation, you actually imply that there are R equations, one for each component for gamma. And f is not one function, but actually R functions. Okay. The important point is this f, this function, essentially has all the information about the group. Right? Well, actually, it's not really all the information about the group, but almost all the information about the group. Basically, because remember, we are only talking in terms of parameters. Parameters means you have imposed a chart on your manifold. Okay, if you remember the differential geometric language. Now, the chart may not encompass all of the manifold. That is, the group may not be possible to impose nice coordinate systems over the entire group at one go. So it may be only a piece of the group where you're actually using these parameters. So this will of course work only when A and B are inside that piece, and so is C. Okay. So actually, this will actually work within the neighborhood of the identity, but whether it will work all over the place is something which is not really clear at this moment. In fact, it will not work all over the place with a single function f. So saying that f has all the information of the group is a bit of an overstatement. But frankly, as you will soon see, what happens close to the identity is actually quite enough to tell you exactly about what happens all over the group in a Lie group, modulo some topological factors, which we are going to perhaps talk about if we get time later. Uh, the important thing is F has almost all the information about the group, if not all the information. So this function is, of course, a very important thing to talk about. Well, it turns out that the function happens to be pretty complicated to write down in most situations. Like, for example, if you imagine rotations, what kind of parameters would rotations have? You have studied something about rotations before, right? If not as a rotation group, or
Euler,
at least as a rotation group, you have
Euler
definitely
angles.
Euler angles, right? That would be one possibility. So one rotation will be given by a bunch of three Euler angles, theta phi psi, so theta 1 phi 1 psi 1 for the first thing, and theta 2 phi 2 psi 2 for the second thing, right? So this function for the SO3 group should be able to tell me, if I have these two rotations done one after the other, how is the overall theta for the composite rotation related to theta 1 phi 1 psi 1 theta 2 phi 2 psi 2? How is the overall phi related to theta 1 phi 1 psi 1 theta 2 phi 2 psi 2, and so on? That function does exist, but it's really not a very, very simple function to use. A bunch of functions right now. Okay? And things get even more complicated for more involved groups. Having said that, there are ways in which you can extract properties of the function, especially the way the function behaves close to the origin. Origin is important because remember, origin stands for the identity in the group. So to figure out how the function behaves at least close to the origin is going to turn out to be very important. And for that, we will now have to take a look at various properties of the group, which will actually put restrictions on F. You cannot just take any old function off the street and call that a function which talks about the composition group for Lie group. There are restrictions. Some obvious restrictions. For example, you know that any group will have to obey this. Okay, let me write the thing out at the top. The important rule, which is AB equal to C, implies parameters for C is this function if of alpha, which are the parameters of A, and beta, which are parameters of B. Now, having said that, this rule, which is true for all groups, right? What will that tell me about the function?
It's A or zero. I think it's A, right?
This is A, this is A. Oh, sorry, that's not zero, that's A. Yeah, I tried to write A, by autocorrect got, or this is not an autocorrect, this is a pattern recognition thing on what I'm trying to draw. Made it into a zero. Okay, so this is A, of course. So what does this tell me about this function F? It tells me something very obvious, right? Identity. What are the parameters for the identity?
Zero.
Zero. If you put alpha, zero and alpha as inputs, that is of course R zeros and alpha 1, alpha 2, alpha R. What are you going to get?
F alpha semicolon zero.
Yeah, if alpha semicolon zero, true, but
Alpha
equal to
only.
alpha, right? So if you put in zero on one side, okay, zero for any one of the arguments, either the first one or the second one, the other argument comes out. Has to. Okay, this function F has to have this property. So even this tells you quite a lot about the structure of the function, at least for small values of the parameters. Now, if the parameters alpha, beta are small, this is something we are going to look at later in some detail, but let me just raise this point right here. If parameters are small or in a complicated function, say fj alpha semicolon beta, I'm talking about the jth function now. I already know that I should be able to expand this out in powers of alpha and beta and retain only the smallest powers. right? At least I'm making an assumption that the functions involved are smooth. In fact, that's something I should have stated uh, in already, which is this. Um, the defining property of what makes the group a Lie group is not just that you have parameters. A group is a Lie group if this happens. This function f, which defines how you compose parameters with each other to get the group multiplication, must be a smooth function. Function of two arguments. In fact, not one smooth function, of course. There is there a hand or something?
Yes. Yes, so I just wanted to ask, so are we assuming that we are working with a manifold or like some differential
Maybe
structure?
you joined a bit late, but okay. First question, first point. Do not bother raising your hand. Just switch on your mic and ask. Simply because I may not be able to see your hand to a corner. Okay. Now, since you must have joined a bit late, because at the very beginning we said that a Lie group is a group and a manifold, which is why you can put parameters or coordinates basically, which is where you have bunch of R real numbers specifying every group element. Okay, does that answer your question?
Yes, yes. Sorry.
And because now you might, of course, use the fact that we have studied differential geometry earlier and talk about how do you define differentiability of functions and so on. Here we don't have to bother about this, right? Because this is a bunch of real numbers. Two are real numbers, right? And gamma is also a real number. These are real functions of multiple real numbers. So differentiability is just ordinary differentiability. So basically what we have done is instead of using, uh,
Sir,
yeah,
sir, is the manifold CK or C infinity?
I don't care. It's actually, it's just CR is all you need. It's C infinity actually for most practical purposes. Depends. Actually, we don't need it to be C infinity. We will see that most of the results will go through if it's just C2. There's twice differentiable functions are all you need. But for most Lie groups that we actually deal with, they are actually C infinity groups. So that's really a distinction that will not be that important for us. All I'm saying is these are really R functions, real valued functions of two R arguments each. So we can just use standard calculus, that is multivariable real number calculus, to tell us what functions, what differentiability means. What this really says is that the operation of multiplication in the group manifold is a differentiable function. But we don't really want to go into that. Now, if you have small parameters, let's come back to this. You should be able to. Okay, there, by the way, sorry, before I proceed, there is another part of the definition of the group, Lie group, another thing in the definition of the Lie group, which is this. There is one important property of the group that we have not talked about so far. In fact, we have only talked about one property, the existence of the identity. We have not talked about the associativity yet. We will soon. And we have not talked about uh, the existence of inverses, right? So for every element A, which is composed of alpha 1, which basically has parameters alpha 1 to alpha r, there will be an A inverse. And the inverse, let's say, has parameters alpha tilde 1 to alpha tilde r. It's an additional defining property of the Lie group that the function which tells you how to relate alpha tilde 1 alpha up to alpha tilde r to the original alpha 1 to alpha r. There has to be such a function, right? Which actually is related to this function. But anyway, it says that this mapping, which maps the alphas to the alpha tildes, must be a smooth function. Again, what order of smoothness? Second order is mostly what we will need, but we will assume infinity order for most cases. So having said that, if this were a smooth function, what would the expansion look like? This has nothing to do with group theory. This is basic, basic theory of functions, real analysis. If a function, say, okay, let's start with this. Suppose I have a simple function of x and y. If I expand this out, what will it look like? Taylor series, nothing else. What will it look like? Taylor series of two variables. Anybody remember that? I'm not even asking you for what the coefficients are. Just tell me in terms of coefficients, C0, C1, C2 will do.
It's just hx0, y0.
So let's do with 0, 0 to begin with. Let's keep
Let's
that
say
simple.
h00.
H00, okay, H00 is some constant H0
Yeah.
plus
Plus del h del x.
del H del X at the origin. So let's call that C1
Yeah.
plus C2y
Yeah.
plus then you have higher order terms. Say d1 x square by 2 factor, or it doesn't matter. d2 y square plus d3 xy and so on. Right? Okay? And also higher order terms. Now suppose H has this property that H0y is always y. And Hx0 was always x. Can you tell me what that will tell you about H0, etc.? What will H0 be?
H0 will be E.
You're confusing the group element with the parameter. These are numbers. First of all, there's no E here. There's just any function I'm talking about. I'm not even talking about the group function. I'm just saying, suppose you had a property like this.
Okay, H00 will be 0 then.
H0 will be 0. Right? Because all you would need to do is H0 is H at 0, 0. That's of course 0. Okay. What can you tell me about C1 and C2?
There'll be 1.
Right. If you put in y equal to 0, for example, then all these terms will go away. The y terms with y's. Okay. So you will be left with x, c1x plus d1x squared and so on. And this immediately tells me that c1 has to be 1. Right? So that you get x. And this has to be 0. Okay? Right? Is that clear to everybody? All you do is put y equal to 0. Put y equal to 0 and see what happens. You need to get x, right? And then what else can I say? What about this condition? If you put in x equal to 0, what happens? You put in x equal
C2
to
will be 1.
okay, so you get C2 will be 1 and
Or higher order terms containing only y would be 0.
yeah, this will also be 0. But you cannot say that this will be 0, right? So basically, and it's up to second order, this will be x plus y plus some constant. I keep on calling d3 xy, right? Okay. Of course, what it doesn't rule out at a higher order, let's say at the cubic order, you can have terms like okay, I'm not even bothering to write down the coefficients, but you will have terms like x square y, xy square. But what you cannot have are terms like x cube alone or y cube alone. Okay. Because a term with x cube alone will not vanish when you put in y equal to 0. And then x comma 0 will not come out to be x. Yeah. So if you make a demand like this on any function, it severely restricts its expansion, Taylor expansion. Right? So can anybody tell me what the Taylor expansion for my Fj alpha semicolon beta would be? Remember, the same condition holds, right? If you put alpha equals 0, you just get beta. If you put beta equals 0, you just get alpha. So one thing is sure, there can be no concept, there cannot be any term independent of alpha and beta. Right? In fact, what should the first order term in alpha be? In general, it should have been something like alpha k c k j, right? But it has to be alpha j. And then you can have some a j k l. Where it's important that in this term, neither k nor l is 0. Sorry, alpha k b, these are not powers, these are just I made a mistake. Sorry. Alpha to the k is, of course, alpha k is not a power of k, it's the kth alpha. So this is fine. Alpha k beta l, terms like these, they can always be there. But no term which has only alpha k, terms like alpha k alpha l with coefficients, or beta k beta l, they will not be there. Plus higher order terms. Is this clear to everybody? Because this is the only way in which if you put in beta equal to 0, you're going to get back alpha j from here. And when you put in alpha equal to 0, you're going to get back beta j. Make sense? Yes or no? If it's no, tell me.
Yes, sir.
Yes, that meaning what? Meaning it makes sense. You.
Yes, makes sense.
Okay, so this is something we are going to make use of later, this Taylor expansion.
Sir,
For the timing, this is
sir, you
something.
are
Yeah, go ahead.
using small parameters just because the function may not be.
Because I want to write down a Taylor expansion.
Okay.
And because we are talking of terms which are close to the identity. Here, only for this. We are going to come back to this later. So far, we have not said parameters are small, but we have just said the parameters are values which you have within your neighborhood, within that particular neighborhood, such that you have to ensure that the group element which stands for the alphas and the group element which stands for the betas, when you compose them together, you stay within the neighborhood so that you can use the same chart to give it coordinates. That's the only restriction. For that, the parameters don't have to be very small at all. But if the parameters are small, I could do a Taylor expansion, and the Taylor expansion would look like this. Of course, I can do a Taylor expansion even if the parameters are large, but then you couldn't stop here. You would have to also include many, many higher order terms to get an accurate value. Now, this is an aside for the timing. We are going to come back to this particular form later. It's going to be very important. For the timing, let's not worry too much about that any longer. Let's go back to seeking out various properties of this function. But before we do, let's talk about this. Functions on groups. Well, I'm not going to talk too much about that. Only I will say this. Let's say there's a function theta which maps you from G to R, such that theta acting on a group element gives you a real number. And as you change your group element, the numbers change. Of course, this theta of G is the same as theta composite phi inverse acting on phi of G. Let me remind you again, phi of G was the function which phi is a function which gave, when acting on G, the parameters. So this is basically a function capital theta, this composite function, the so-called proxy function from our differential geometry class of the real numbers. Okay, so Xi1, Xi2, Xi are the real numbers corresponding to the group element G. And you are going to get a function, capital theta, which acts on these bunch of real numbers to give you whatever small theta of G gave you. So this is the function that we are going to usually talk about when we say function in the group elements. And let's say if I were to change my group elements slightly, okay, what do I mean by slightly? Here, the important thing is the identity of, if you apply the identity on a group element, the group element doesn't change. So any group element close to the identity, if you apply that to any other group element, the second group element will change, but not very much. You all agree to that? Identity acting on A gives you A, right? Is equal to A. If instead of identity, you use something close to identity. Let's call that delta A for the time being. It will give us something which is close to A. Now, the important thing is, what do I mean by close to the identity? Here we have a nice advantage. We have every element is given by a bunch of numbers, right? The parameters. Identity, remember, has parameters 0, 0 up to R zeros. So I will say an element qualifies as being close to the identity if all its parameters have values close to 0, small parameters, right? There.
Yes.
So what were the parameters close to A prime B? A prime will be F delta A, comma A. Okay, delta alpha, sorry, I should say delta alpha, comma alpha, because delta A, let's say, has small parameters. Let's call those parameters delta alpha 1, delta alpha 2, and so on. And this has large parameters. Large meaning not necessarily small parameters. Okay. Now, what is this going to be like? If delta alpha is very small, we can at least write this approximately up to first order in delta alpha as this. And let's talk about jth component here. Jth component is a jth function, fj, 0 equal alpha, plus del fj del beta k. Everybody agree with this? Plus higher order terms, of course. You take the function f of beta comma alpha, differentiate that partially with respect to the kth beta. Here, beta is the first argument here. So beta 1, beta 2, beta k, beta r are in front. Beta k is somewhere among the first r arguments. You're partially differentiating with respect to that, putting beta equal to 0 at the end. Of course, alpha is whatever it is, and you get multiply that by how much beta changes. So beta was 0 to begin with here, 0, 0, 0, 0, 0. Then it has become delta alpha 1, delta alpha 2, delta alpha k. And this is what you get. Of course, the summation over k is very much implied. Is it okay?
Excuse me, sir.
Yeah.
So why should this necessarily hold that if we multiply with A something close to E, then we should get something close to A?
That's exactly what closeness means in this context, nothing more than that. And you do expect that if your connection between the parameters, now here, what do you mean by close in the first place? Group elements are abstract elements, right?
Yes.
Closeness would mean in terms of parameters being close, right? Now, if your function f is
Yes.
something in which if you put in 0 for the first argument and alpha for the second, of course, first r arguments are all zeros, last r arguments are arguments of alpha, you are going to get back alpha. So if instead of 0, if you put in something small instead of 0, you should get something which is pretty close to what you get when you put in 0. That's exactly, in fact, that is exactly what you see here. What is this? Fj 0 semicolon alpha?
It's alpha.
It's alpha j, right? The jth alpha. Plus a bunch of numbers which depend, of course, on what? What do these bunch of numbers depend upon? Come on. You're taking a function of 2r arguments, differentiating with respect to the kth argument, and setting the first arguments equal to 0 after doing the derivative. What can the derivative depend upon? Then, will it be a number or will it be a function?
It will be a number.
It will be a number if you take it. Okay, the value of a derivative is always a number, but can it depend on something? Or it will be a constant? Will it be a constant number? For a given function, given k, given
It will
fj,
depend on how the function depends on
oh,
beta
that's
k.
okay. I'm saying for a given function, can this number depend on anything else? Suppose the function fj is given, the j, k, all these are known, fixed. Then is it possible for this to change? Okay, first of all, let's put the notation. We call this eta. This is a standard notation, eta jk. Right? It will depend on j and k, of course.
It can depend on alpha, I think. Right?
It, of course, not can. It will definitely depend on alpha. Right? Because you're just putting the first R argument 0. The other arguments are very much there. Right? So this will be function, not a number. This will be function of the R alphas. Let me just write down the definition once again. This is going to be very important, the eta j case. So let me just okay, let me write that in red. Eta jk alpha are functions, of course, R square functions. J and k each can take R values, defined to be the kth the partial derivative of fj with respect to beta k. But fj, of course, is a function of both beta and alpha. I'm writing beta alpha explicitly to ensure that you can see that the betas take the first argument, and alpha sit after that, and then you put beta equal to 0. All the betas equal to 0. Okay? So this tells you how the function changes with beta, but when beta is 0. Or at least changes with beta when beta is very close to 0. Right? Of course, the rate at which it changes does depend on alpha. And this gives me the expression that fj delta alpha semicolon alpha is equal to alpha j. In fact, I'm just writing that same thing again. Alpha j plus eta jk depending on alpha times delta alpha k. Summed over k, of course. I hope this makes sense to everybody. Oops. Right, we should draw a line. But this is a very important equation. So let's put this in a block. At beta equal to 0, that's important. This is a very important equation. Now, first of all, the eta jk's, of course, can be derived from the f's. If I know the f's, I can find the eta. But can anybody tell me why the eta? I would claim that etas are simpler than the f's. Can you see why? Any idea? Okay, how many arguments do the f's depend upon?
F depends on beta, whereas eta does not.
Well, f depends on two R arguments. On the R arguments of beta, R arguments of alpha. Whereas eta only depends on the R arguments of alpha. So it's a simpler function, less variables. Okay. It turns out that if you know these functions, you can actually say a lot about the nature of the group. We will see how soon. But before we go there, let me just point out one thing. Can anybody tell me what these are going to be? That is, if you put alpha equal to 0 here, then what are these derivatives going to be? Notice that since the derivatives are going to be done with alpha held constant anyway, right? That's what a partial derivative is calculated by. It does not matter whether you put alpha equal to 0 before you do the derivative or after you do the derivative. In fact, if you go look at first principle values, the way in which you work it out using first principles, you actually have to put in the value of alpha to begin with and ensure that it doesn't change when you change the value of the kth beta. So if you put in alpha here, what is fj beta comma 0?
Delta
Beta
ck.
That's beta j, and so this result, as somebody was saying, must be delta jk, right? Okay. So if I make a matrix, which is sort of obvious on the notation, I'm writing eta jk. So if you put all the eta jk's together, okay, I get a matrix, right? Let's call that matrix this. Okay, what letter is this, by the way? No, that's a very simple question, right? Come on. Which letter is this? Don't tell me you can't recognize that letter. Okay, of course you agree. All of you understand that I'm asking this because it's not capital H. It's capital Eta, which happens to be the same as the Latin capital H, and is the same structure. This really is capital Eta. That is why actually you give it that name. Now, what can you say about the invertibility or otherwise of capital H alpha? Can all agree on one thing, right? Capital H 0. What matrix is that?
Identity.
Which identity? Size?
R cross R.
Yeah, it's an R cross R identity matrix. This is definitely invertible, right? No question about that. So for a parameter value of 0, H is invertible. Since H is defined through these eta jk's, which are derivatives of f, and f we have assumed to be smooth, so the derivatives are also smooth. So at least continuity, so etas should be continuous functions, right? And if etas are continuous functions, then at least this will follow. A neighborhood of 0 for which is it okay? In other words, if the determinant is 1, not 0, but it's 1, when the parameter is 0, if you change the parameter slightly, the eta jk's are all going to change slightly. So from 1, it will not jump to 0 all of a sudden, right? There will be a region over which it will stay non-zero. Is that okay? Determinant of this matrix H alpha is 1 when you start at alpha equal to 0. And since it's a determinant is a continuous function of the elements, and the elements themselves are continuous functions of alpha, there has to be some bunch of a region around the origin for which determinant of H will not vanish. So H would have inverses. And inverses we will write as psi. So we will essentially say that you have elements or functions of alpha like this. Or eta JL. And well, psi, when you put them together, you get the matrix capital Xi. Well, that's just notation. Just like when you put the etas together, you have the matrix capital Eta. Here you have a capital Xi, which is, of course, capital Eta's inverse. Okay. The claim is that not the claim, this sort of follows immediately from the definition that there is a neighborhood of this region where you will have an H will have an inverse, and this inverse matrix will be called Xi, which will of course depend on alpha, and the components of the matrix are the Xi JL, so Xi JKs, whatever you want to call them, which will of course all be functions of alpha. Okay. So etas and xis will play a very important role in what I'm going to talk about. I will just indicate to you where we are going with this using trying to talk about the other properties of the group. So associativity. AB is CAB, right? And if A corresponds to alpha, B corresponds to beta, and C corresponds to gamma, what does this equation tell us? And you may transcribe this in terms of parameters. What will this mean in terms of parameters? If C composed with AB, right? When you compose two elements, the parameters get hit by the function f. So what does the left hand side say? C corresponds to gamma, alpha, and beta. So what does the left hand side say in terms of for my function f? Yes? Function f applied to what? What should the first argument be? Here, what will it be? What?
First one will be gamma.
What about the second argument? Second argument will be the parameters corresponding to AB. What is that? What is that? What are the parameters corresponding to this? Come on, what is the parameter corresponding to AB?
F of alpha beta.
Yeah, that's exactly what is written there, right? And this has to be equal to what? Clear? So the important point is, it's all very nice to say, okay, Lie groups, group element, this is a group which has every element has parameters corresponding to the element, which means basically like it's a manifold, so every element has coordinates. And there must be a function which tells you that how to compose two elements in terms of the parameters. All very nice. But that function is very strongly constricted. We have already seen that the function has to satisfy the result that whenever I put in 0 for one of the arguments, you must get the other argument as a result. That follows from the group's basic property. Another of the basic properties of the group, associativity, tells us this, that f has to be strongly constrained in this manner. No matter what alpha, beta, gamma you put in, this has to always hold. We will see in the next day that this is going to put in a huge restriction on the way f can change with its parameters. Notice that, oops, where did my page go? Okay, I might lost the page somehow. Something is going to some funny places. Anyway, doesn't matter. Notice that we define eta jk alpha as del fj del beta k beta semicolon alpha at beta equal to 0. So this is telling me how f is going to change with beta, the kth beta, at or close to beta equal to 0. The condition that I wrote down right now, the associativity condition, will actually be able to give me things like this. Any alpha, okay, the result you will see. I will prove this the next day, hopefully in person. Okay, I'm not going to claim that I've proven this, I've just written this down. But notice that if you know the etas, note that if you know the etas, you know the size, right? Because etas together form a matrix. That matrix is invertible. The inverse function, if you invert it, you get the components, and the components are these function size. So if you know the etas, then you automatically know the size, and this formula tells you that etas, if you're telling you how the function changes when you're close to the origin, is actually ending up telling you how the function changes everywhere, because here this is not alpha equal to 0. This is any alpha. Got it? Now this is an important result. You might try to figure out how this translates to this. That might be a fun thing to try to figure out yourself. How this equation, hint, take a derivative and put gamma equal to 0 after taking the derivative. If you do that, you should be able to end up deriving this result. Important point, what happens close to the origin, which is what eta jk's tell you, is sufficient to tell you what happens elsewhere as well. This is a basic feature of Lie groups that we are going to exploit and dig into. Okay, I'm out of time today. Let's call it a day. Next day we are going to take a look at these the properties which will follow from the associativity condition, and hopefully we will be able to get to Lie algebras by that time. See how Lie algebras follow from Lie groups.